Hi, today we're looking at section 8.2, Arithmetic Sequence and Partial Sums. So we're going to go through some new notation today and work through some problems and a few new models. So the first thing I want to look at is the definition for arithmetic sequence. An arithmetic sequence is a sequence, so we know from our previous units that that's a list of terms in a specific order connected by a comma. And in this particular case, an arithmetic sequence, it's connected where each of the terms have a common difference. And so the consecutive terms, we use the term or letter D to represent those common differences. So position 1, position 2, position 3, position 4, all the way out to some position. This could go on forever. But if I take the second term minus the first term, the third term minus the second term, the fourth term minus the third term, and so on, every one of those subtractions, every one of those differences will be the same. And that's what the common difference is. So as I look at this pattern, if a sub 1 is my first term and a sub 2 is my second term, then I should be able to take whatever is in the position of my first term and add whatever that common difference is to it, and that would get me whatever a sub 2 is. To get a sub 3, I would take the first term, but now I would add 2 of the common differences to it to get the third term. And if I'm at a sub 4, I would take my first term, and now you can see I have 3 common differences, so I'm going to add 3 times the number of, 3 for the number of common differences times the difference. And so this pattern lets us build the model for arithmetic sequence. A sub n representing any number in the sequence equals a sub 1 plus n minus 1d, and that n minus 1 notice comes from right here. If I said I had 3 common differences, that's 1 less than the term itself. If this one was 2, then that's 1 less the term itself. So that's what that n minus 1 is representing. And this is a model you would definitely want to use if you're beginning at 1 and moving through the model or the sequence. So as we look at problem 1, we have an a sub 1 term or a beginning term of 2. They are telling us, or we know, the common difference, and I want to find the nth term. So remember, what does the nth term mean? That means you're writing a model because you don't know the exact placement and you want something that represents all terms in the sequence. So we're going to start by using our model here. So a sub n equals a sub 1 plus n minus 1d. That's what we just kind of created from our pattern a moment ago. And then we're going to plug in our information. So we know a sub 1 is 2. We know the difference is 3. So then to clean this up and give the explicit model, then I'm going to distribute 3 here, distribute 3 here, and I get 2 plus 3n minus 3, which gives me an nth term model of a sub n, because we've got to use good notation, equals 3n minus 1. If I want to find the number of terms in the sequence, let's say find the first 5 terms, then I already know what 1 is. So then I could put 2 in my model. 3 times 2 is 6, 6 minus 1 is 5. Then I could put 3 in my model. 3 times 3 is 9, 9 minus 1 is 8. Then I could put 4 in my model. 3 times 4 is 12, minus 1 is 11. And then I could put 5 in my model. 3 times 5 is 15, minus 1 is 16. And that would allow me to generate the list of terms in my sequence, remembering that this would be a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. So keeping in mind that an A with a subscript represents a position in the sequence, where an S with a subscript represents the sum of those terms. So number 2, we have an a sub 4 term, which is 20, and an a sub 13 term, which is 65, and we're asked to find what the first term is. Now I know some of these numbers today that I'm giving you are easy and simple numbers to work with, and you might even be able to crunch the numbers in your head. But what I want you to remember is I'm giving you small, easy numbers so that you have some common sense about this and you have some number sense to know if your answer is correct or not. So know that I will expect every single time you working the models on your paper, no matter how brilliant you are and what you can do in your head. All right? So here's my model that I'm going to continue to use for arithmetic. I'm going to be able to plug in some numbers, except that it's not exactly the numbers I have, right? I'm going from 1 to some term. I don't have 1. So if I'm not using the model as it is, we do need to make a couple of adjustments so we can continue to use the model. So here's how I'm going to work through this problem. I'm going to start with my smallest number, which is a sub 4. That's what was given. And I'm going to replace a sub 1 with a sub 4 in my model. Then I'm going to end out here at a sub 13 instead of a sub n. So when I do that, since I'm not beginning with number 1, it's really just as easy to count. How many common differences are there between 4 and 13? Well, that would be 9. And so I adjust, instead of doing n minus 1, I'm actually just going to adjust because I can count that very easily. And then I won't accidentally make a mistake and be calculating the wrong number of differences times whatever d is. Okay? So then as I go through finding d, I would plug in the 20 for A4, the 65 for A13. I know I have 9 common difference, so then I can actually solve this for d. Move the 20 over, I get 45. Divide by 9, I get 5. So now I know what the common difference is. And remember that 9 comes from how many common differences between a sub 4 and a sub 13. So once I am confident and I know what my common difference is, I can go back to my model and I can plug in what I know and actually work through finding a sub 1. So if I have a sub 4 out here, you could use a sub 4 or you could use a sub 13. I typically pick the smallest one that I can find. Just makes the math a little easier, especially if you're doing this without a calculator. And then I plug in what I know. I don't know a sub 1, but I do know a sub 4 is 20. I know that there are the differences we can do n minus 1 here because look, I am starting with 1 this time. So I get 4 minus 1, which is 3. So 3 times 5 is 15. 20 is what a sub 4 is. So when I move the 15 over there with the 20, I get 5. And now I have solved for a sub 1, which is what we were asking to do. There were small numbers. These are small numbers again, so you can kind of keep an eye on what you're doing and have some realistic expectation. I would not expect small numbers on the test because I'm going to want you to actually show me that you know how to use and work with the models. All right, number 3. So I'm given a sub 1 is 5. I'm given a sub 4 is 15. I want to find the nth term. So remember when we see find the nth term, that means we're writing a model. So that's always where I want to start so I know where I'm going. And then I look at what I have and I decide what's missing because that helps me clue in as to what I need to find to be able to finish the problem. So I know I have a sub 1, so that's covered. That's just 5. What I don't see in my given information is what d is. So that's what I need to calculate. I need to figure out what d is. And again, I'm going to use my models to do that. So I'm going to have a sub 4, which is a sub 1, and then plus 3n because there's 3 common differences. And then I am going to move the 5 over. It's 10. I'm going to divide by 3, so I get a fractional difference, which is 10/3. So now I'm going to go back to my model, the same one we've been using. I'm going to plug in what I know. So I am plugging in a sub 1, and I'm plugging in the difference over here, which is 10/3. And so I need to distribute the 10/3 through here and here, and then collect like terms. So when I distribute 10/3 through, I get the 5, and then I get 10/3 n minus 10/3. If I want to combine my like terms, that means I need to put the 5 together with negative 10/3. To do that, I need a common denominator. So my common denominator has to be 3. So the quick way to do that is take the denominator, which is 3, times the whole number, which is 15, and put it over that common number you're looking for. So this is 15/3 minus 10/3. So that's going to let me go from there and have 5/3. So I have 10/3 n plus 5/3. Remember, good notation means you would say equals a sub n because we're finding the nth term. So that's where our model comes from. Okay, so on number 4, we have a sub 4, which is 16. We have a sub 10, which is 46. And I'm trying to find the first 5 terms. So this time I'm not finding a model, I'm finding a list. And the list will all be connected with a, you got it, comma. All right, so what do I have? Well, we don't have an a sub 1, so that's an issue. And we don't even have a difference. So we got to do a little bit of calculating here. So the first thing we're going to find is the difference. So we're going to use our model, but remember the smallest number is 16, so I'm going to start with a sub 4 and go out to 46, which is a sub 10. So there are 6 common differences between 4 and 10. And so then I have 46 from my given, 16 from my given, 6 that I just calculated for the common differences d. So I move the 16 over, that's 30 equals 6d, divide both sides by 6, so now I know what my common difference is. It is. Okay, so now we have our difference. So we're going to use the model to create a model that we can use to find our terms. So I go back here and I have now, I'm going from a sub 1 to a sub 4, and so I can use the n minus 1. So that tells me I have 3 common differences, and 5 is the difference we just found. So as I calculate this, I move the 15 over to 16, and I know that a sub 1 is my term. So then, if I know what a sub 1 is, I can add the common difference to it. So I don't need to write the full model. I just needed to figure out where I needed to start from. So a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. So that's 1 plus 5 is 6, 6 plus 5 is 11, 11 plus 5 is 16, and 16 plus 5 is 21. And so that gets you the 5 terms. So I went ahead and identified them in their position right here, but that's the first 5 terms of the sequence. All right, so question 5, we're given a sub 1, which is 5, a sub 2, which is 11. We're finding a sub 10. So notice this time we're finding a position. So that's not a list, that's not a model. So what do I have? Well, I have a sub 1, so that works nicely for us. I don't have the difference, so what do I need to find? I need to find the difference. So to do that, I don't have to go through the model on this because I have consecutive numbers, right? If I have consecutive numbers, then I know I can take the second minus the first, and so I get 11 minus 5, which is 6. Easy, easy, easy way to find the difference. And so now I'm just going to apply it to the model. So I'm going to have a sub 1, which I know is 5, so I can plug in there. I'm finding a sub 10, so remember I'm using the right notation. A sub 10 is a position, S sub 10 would be a sum, and then I have 5 plus the number of differences is 9 times 6, so 5 plus 54 is 59. Okay, so switching gears real quick, let's do a couple of real quick reminders about series. In arithmetic series, we have 2 models that we need to know, and these 2 models are to determine partial sums, which you should recognize because it has S in a subscript. Yes, you do need to know both models because you'll use the models at different times. This is what I call the short model. The short model you will see in anytime you have the first term and the last term. You've got to know the last term over here. This model, if you'll notice right in here, looks very similar to the arithmetic sequence model. The difference is you use 2 a sub 1s. Okay? So a sub 1, 2 a sub 1s, this kind of looks like the model. It's easier to remember that way. But in this particular model, you do not need the last term to be able to accomplish what you want. And there are a lot of questions on the assessment where you don't know the last term. And it's a little bit longer if you try to use the short term in those particular situations because you have to calculate what the last term is and then you can use this model. Whereas this model over here, you don't have to calculate the last term. You can just plug in what you know and go from there. So for example, on this one, here's number 6. So we have 0.5, 0.9, 1.3, 1.7, dot, dot, dot. Find the sum of the first 10 terms. So what do we know? We know that we're finding 10 terms because that's what the problem is telling us. We know our a sub 1 term because that's the first in the list. We can find our difference easily because I have consecutive terms, and when I can do consecutive terms, I can take the second one minus the first one, so I know the difference is 0.4. What I don't know is the last term, the value of the last term. So in this particular model, I worked it out both ways just so you could see the two side by side. In this one, I didn't know a sub 10, so I had to calculate it. So I had to use my model. I had to figure out what a sub 10 was. So I used my values of a sub 1, which was 0.5. I knew there were 9 common differences. I knew the difference was 0.4, so I crunched my numbers and I got this. Once I get a sub 10, now I can go to my summation model, my partial sum model, and I have my first term, my last term, 10 divided by 2, and crunch the numbers and I get 23. So a caution for this is now you have to remember and be very meticulous with 2 different kinds of notations because you have to have the notation up here that shows you're calculating a specific term in the sequence, the last term, and then you have to have your summation notation down here, the S subscript, because you're adding things up. So you have to be super duper careful here and make sure that you don't confuse these notations or forget to use the right notation. If I use the second model, I don't have to worry about all that. I just plug everything directly in because I don't need to know what the value of a sub 10 is. I can crunch my numbers and you can see I get down to the same answer with a little bit fewer steps and fewer things I have to worry about in terms of notation. Okay, quick review of sigma notation. So here's my sigma. I have n equals 10 up to 100. So lower bound is 10, upper bound is 100. Sequence is 6n. So I want to find the partial sum without a calculator, and then I want to verify it on the calculator. So to do that, I need to do a couple of things. Remember, to use the short model, I need the first term and the last term, and that's easy to calculate on sigma because the lower bound is the first term that you're plugging in, and the upper bound is the last term you're plugging in. So to get a sub 1, I plug in 10. 6 times 10 is 60. Super easy. And then I take the upper bound, which is 100, and I plug in 100 here for n, so 6 times 100 is 600. So I have the first number, I have the last number. That would need to be in your work. So then when you're going to figure out how many n's, you typically want to say, you know, okay, well, I'm going to do 100 minus 10, so that's going to give me 90, but don't forget to count the 10. When you subtract, it's not counting that initial value, so it's actually 91 terms. And then I go to my model. So my work is going to have an a sub 10, it's going to have an a sub 100, it's going to say what n is, and then I'm going to see my model work. So I'd have 91 over 2, 60 plus 600. This is a fraction that can be simplified. 2 goes into 660 330 times, and then when you multiply that out, you get that. And so then remember, when you're doing your calculator, you would go alpha window, and you would get number 2 notation, and then your lower bound in a calculator would be x, and you put a 10. Whoops, I went to the wrong spot. Let me get back down here to my lower bound. 10, and then the upper bound is 100. And then I will go out here and I will put 6x because x is the variable I'm using, and I get the same value that we just calculated. Okay, so then we move on to the next one, 8. And again, this one is 1 to 20. So we're finding the partial sum and then verifying it with the calculator. So I need to calculate the lower bound. So I put a 1 in here. 2 times 1 is 2. 2 plus 5 is 7. And then I put a 20 in here. 2 times 20 is 40. 40 plus 5 is 45. So that means I've calculated the first term and the last term. How many n's are there? Well, there's 20 minus 1, which is 19. And then you would add 1 to it. So I have 20 for my n. Then I go to my model, and I have 20 over 2, and I have 7 plus 45. So 10 times 42 is 520. And I probably should have had the notation be s sub 20 here since I am adding those up. And if I go to my calculator, we can verify on the calculator. This is what we would put in. We would put in an x for our lower bound, and I do get the same value on my calculator. All right, so it sounds like we're getting a little serenade in the background. If you can hear the violins going, we're having the art and music walk tonight, so you get a little extra in your video for your enjoyment, I suppose. So here's the last one, an application taking you through a scaffold problem. So the problem is a bowling league tournament with 12 bowlers. First prize is $1,200, second prize is $1,100, third prize is $1,000, and they're going to give that money out all the way down to those 12 bowlers. So the first thing I want to do is write a sequence. So my sequence might look something like that. You could, think about going down to the end. We're not necessarily giving out all the money. We're just giving out enough so that each bowler gets their share of the prize. All right, so the first thing we're going to do is write an a sub n model that represents the cash prize based on n, where the bowler finishes. And so to do that, we're going to use our model. And so I have a sub n equals a sub 1 plus n minus 1d. And so I know from my problem the first bowler is the 1,200 guy, or lady, so they get $1,200. And then we don't know what the common difference is, but super easy to find because, again, we have consecutive numbers, right? So 1,200 and 1,100, just remember to subtract in the right order. 1,100 minus 1,200 gives me a difference of negative 100. If you subtract in the wrong order, you're going to get positive 100, and that's not going to work well for the problem. So make sure it's second term minus the first term. Then we go to our model. We plug in what we know. We distribute that negative 100 through so we can collect our like terms right here, and we now get a model of a sub n equals 1,300 minus 100n. And the last part, part C, says find the total amount of prize money awarded at the tournament and check that with the calculator. So again, as we're working through this, and I went ahead and went through it with both models just so you could see in case however you decided to go. So the prize for 12th place, that means the 12th place, would be a sub 12. So that is the 12th place, right? And so I have 1,300 minus 100 times 12. So that means a sub 12 is 100. If we're going to use the short model, remember, then we have to know the value of the last one and the value of the first one. So now I can switch from a sub 12 to s sub 12, and I can get my sum. And so I have 12 over 2, 1200 plus 100, 6 times 1300 gives me 7800. And that's what S sub 12 is. So remember, when you're doing this model, you have to be conscious of using the right notation. You have to have the value of A sub 12, and then you have to have the value of S sub 12. So you have to make sure you watch that notation, which just means that you're giving out $7,800 of prize money at the tournament to the 12 bowlers. Now, if I went the other way, where I didn't need to determine what A sub 12 was, then I use this model. I plug everything in where it goes. I distribute through. I collect my like terms. I get down to 6 times 1300, which means S sub 12 is again $7,800. Don't forget it is money, so I would expect to see the appropriate units anytime you're talking about a word problem. And this might give you an idea of how they would scaffold the questions through. All right, so I hope that wraps up everything that you need to know. Don't forget, on the Canvas under Unit Resources, there is a help sheet for Sequence and Series unit, which also has like Pascal's triangle and some other things that we're going to do, but it's all on one sheet. So if you need the models, these are 3 of the 6 models that will be on your speed quiz, which we will take after we finish Geometric Sequence, Series, and Partial Fractions, which is next class period. Bye, guys.